Rock, like jello, can be squeezed when we put it under stress. But when that rock is being squeezed in one direction, where does it actually go? Two things may happen, and often they're happening in combination. First, if there's space, the rock will just bulge out in the other two directions. And if there's no space, rock will actually build stress in the directions perpendicular to the direction of the load that is being applied. This transfer of deformation from one principal direction into two orthogonal directions is what we call the Poisson's ratio. We're going to measure the Poisson's ratio in three different ways. First, we'll take a deeper look at what happens with jello in our previous Young's modulus test. Then we'll look at wood and rock and put that as in a load in a vise. And finally, I'm going to some extreme measures on a sample that I've been meaning to break for a while.
First, a little more theory. Like the Young's modulus, the Poisson's ratio can be measured in a simple uniaxial compression test. A load F is applied to an area A along a cylindrical core sample. The sample shortens due to the load, and the strain represents the relative shortening of the sample's length. As another result of this actual load, the sample bulges. The radial strain represents the relative increase in the radius of the sample. The Poisson's ratio simply represents the ratio of the relative radial expansion to the relative actual shortening. More generally, Poisson's ratio links deformation in one direction to deformation in another direction. When we measured the Young's modulus of jello in a generic gelatin, an additional observation was that the samples were bulging. While the shortening and bulging are somewhat nonlinear, on a large scale we see the following. Jello becomes 31% shorter while bulging about 14%. That's equivalent to a Poisson's ratio of about 0.43. And gelatin becomes about 29% shorter under a load of about 5 pounds, while it's bulging about 13%. That's a Poisson's ratio of 0.44. We can also put a sample under stress in a vise. In this vise, we can apply about 1,000 pounds of force on a sample. I can measure the sample's shortening and bulging with a caliper. For example, in cork, we can measure the shortening of the sample, but we almost see no measurable bulging in the horizontal directions. For more sensitivity, I can also put strain gauges on these samples and measure the relative shortening of the sample's length and the increase in the sample's radius with these strain gauges. In oak, the sample bulges about 1/3 of the shortening. While for sandstone, I actually broke the sample, most likely due to not applying a uniform load. I can't really do this, I really need a lab for this. For proper measurements, sample or sandstone would bulge about 1/5 of its shortening, and in shale that should be about 1/3. So the typical Poisson's ratio of sand is about 0.2, typical Poisson's ratio of a shale is about 0.3. To create larger deformations, I need a bigger vise, or of course go to a regular laboratory. Or we can increase the load by parking a quarter of my truck on top of the sample. That should definitely help me win the battle to achieve a measurement of the maximum compressive strength of jello. We can now compare the measurements we discussed to determine the Poisson's ratio of these materials. In a radial versus axial strain diagram, the slope in this diagram represents the Poisson's ratio. We see a slope of about 0.43 for jello. At higher stresses, this material starts to behave like a liquid with a Poisson's ratio of 0.5. For cork, we see a Poisson's ratio very close to 0. So no radial expansion when we're putting the cork under axial stress. For oak, we measure a Poisson's ratio of about 1/3. And then finally, for sandstone, if this would have worked, we would have measured a Poisson's ratio of about 0.2, and for shale about 0.3.
Shale power beats jello. Woo! In all seriousness, in conclusion, the Poisson's ratio of rock is important in assumptions we make about fracture growth. First, the 3D state of stress, how does the weight of the overburden transfer into horizontal stresses against which a hydraulic fracture opens. Secondly, the difference between two horizontal stresses, as determined by tectonic stresses and the Poisson's ratio induced stresses, is an important parameter in understanding the degree of complexity in shell fracks. And finally, the closure stress in individual layers of the fracture that the fracture will encounter as it grows in height determines how the fracture may be confined by these stresses as induced by the Poisson's ratio differences between shales and sands. Now, for more information, visit us at libertyfrac.com. This is Lane at Liberty. Thank you for watching.